we didn't have time to do it, and I don't have enough room to clutter up the board explaining it. But it's going to turn out that if we multiply our acceleration in radians per second squared by our radius, we get the acceleration in the direction of the arc. So that the speed of this object, if the beam is accelerating at 4 radians per second, 4 radians per second squared, if the beam's accelerating at that rate, then something 40 centimeters out along the beam will change at this rate. And I could have easily enough, and probably should have, let me clean up that smudge a little bit while I'm at it. Probably going to create another one. That didn't help much, did it? 40 centimeters per second. Multiplied, and it's not 40 centimeters per second, it's 40 centimeters per radian. Let's get that right. Formal calculation, 40 centimeters of arc per radian multiplied by 4 radians per second squared. The radians divide out, gives us 160 centimeters per second squared. Then what we're asked is how much force would be required at a point 10 centimeters along this beam to accomplish this acceleration. So what we have here, we have an axis of rotation. Here we have our beam, here we have 40 centimeters, and here we have our mass, which I'll just call M. If we apply a force here, that's going to accelerate this mass. Now, we do have the condition that there's negligible mass in this beam, so that if we apply a force here, we're just accelerating the mass. The beam has no significant mass, so it kind of accelerates for free. Okay. Now, how much force would we have to exert on the mass to give us this acceleration? Well, take the 100 grams, multiply it with this 160 centimeters per second squared, we get 16,000 dynes, or 0.16 newtons. There's something that bothers me about that. 160 times 100. Yeah, it does give us 16,000. Yep, never mind. Okay. 10 to the 5th is 100,000, not 10,000. That was my... Okay, so we get 0.16 newtons, and that force I say from the beam. Okay, well, let me go to the question as it was actually posed. The question was, okay, if we exert a force at 10 centimeters, different than this force. Okay, if we exert the force at the 10 centimeter point, it's going to have to be greater than the force out here. And if we exert a bigger force, a big enough force at the 10 centimeter position, then we can get this beam to accelerate still at 4 radians per second squared. And the force now exerted on the mass is not exerted directly by our force. It's exerted on, that force is exerted on the beam, and the beam exerts a force on the mass. That explains the from beam comment there. We did this in class with a rotating system where you poked it out here. You had some magnets on a strap, you poked it out here, and then you poked it in here, tried to give it the same motion, and you found out that it took more force here than it did here, which shouldn't have been a surprise, but that depends what kind of things you've been poking. Okay. we wanted to develop this in terms of the amount of work done by both of these forces. At least that's what I wanted to do. We didn't have time. It took us a while to get through these ideas, and we really want to get these ideas, so we kind of let that go. And I went ahead and just defined this thing called torque after doing this little exercise. Torque is equal to R times F perpendicular. Okay, where R, I'm going to have to use fancy colors again. R is the vector from the axis to the point of application of our force. So if I exert the force out here, R is going to be a vector 40 centimeters long. Now everybody naturally exerted the force perpendicular to the beam, or to the strap that we were using. Okay, if you'd exerted the force this way or this way, it would have taken more force to accelerate it, but some of that force would have just been pushing into the beam or trying to stretch the beam and wouldn't have done any work. And I'm not going to get into how the work energy thing relates to this, probably until next time. Okay, so we define torque as R times F perpendicular, where F perpendicular means the component of whatever force we exert out here at this position is perpendicular to the R vector. Okay, so there's one definition of torque. There's another definition in your book that's equivalent to this one. They talk about, the line of action of the force and how close that comes to the axis and all that stuff. You can try to reconcile that. The more rigorous and more broadly applicable definition is that the torque is the R vector crossed with the F vector. Okay, so that in this case, here's the R vector, you cross that with the F vector, you get a vector in this direction. That's the direction of your torque, and that's the direction that the torque would be in to accelerate the system in the counterclockwise direction. Okay, well, those are definitions of torque, and we use that definition to kind of shortcut this concept. Now, if you need a force of 0.16 newtons out here, if you're 4 times closer to the middle, it makes a certain amount of sense that you're going to need 4 times the force. It makes a lot of sense in a lot of ways. For example, to get the same motion, you would have to exert the force through the same angular displacement, meaning that the force would have to go through 4 times the distance along this arc that it would along this arc. But if the motion is going to be the same, it would have to do the same amount of work. Well, you can take that and derive the reason that torque has to be defined like this. If torque is what accelerates systems of this nature. Okay? And that's a little vague, but you can kind of store that away. Okay, the thing that isn't vague is that if you want the same torque, now torque is what accelerates the system. Torque is what accelerates a rotating system. We'll see more about that. If you want the same torque, but if R is only 1/4 as great, then F has to be 4 times as great. So that intuition that if you're 4 times closer, you need 4 times the force, that would be the first thing we'd think of. That would be the first thing we'd want to test if we wanted to see if this really works experimentally, as we probably will day after tomorrow in lab. That would be what we want to test, and that is the way it works out. So at 10 centimeters from the axis, we're 4 times as close. We need 4 times the force. We need 0.64 newtons in this case, which is 4 times the 0.16 newtons we would need if the force is applied directly to the mass. Then we can say, just to check, that the first torque we would get from this force here, and let's call that F1, and let's call this F2, okay? That's going to be the 40 centimeters times the 0.16 newtons, and that comes out 6.4 centimeters times newtons, which is 0.064 meters times newtons. Now, I did talk about the way you want to write this as meters times newtons, so you won't be as tempted to call that a joule, because it isn't. The unit is exactly the same, but it's a different quantity. So it's maybe the first time you've seen two different quantities that have the same fundamental units. Torque has the same fundamental units as work energy. However, torque and work energy are completely different things. You have to exert a torque through an angular displacement to do work. And yeah, we'll see that. Okay, the torque of the second, 10 centimeters times 0.64 newtons, comes out the same. So the effect on the acceleration of this system, the rotational effect, the angular acceleration, is going to be the same as a result of both torques. Something you want to kind of get used to. They have the same effect on angular velocity. I initially wrote rotational velocity, and then I crossed that out. That is the way we feel it. That is, but if we want to talk in polite society, we call it angular velocity. Okay, we have a couple of questions regarding the kinetic energy of 100-gram masses at different points along the beam. So we'll address that very quickly in the next video.